will discuss about the derivation of energy equation. This is the subtopic of computational fluid dynamics for third year mechanical students. I am myself P. Venkata Mahesh, Assistant Professor in Mechanical Engineering, Institute of Aeronautical Engineering. Now, the energy equation is governed by one physical law, and that physical law is given here. The physical law is law of conservation of energy. Okay. So what is this law of conservation of energy says? It is based on the first law of thermodynamics, and it states that the time rate of change of energy. Okay. Energy cannot be created nor be destroyed. It can be transferred from one form to another. Now here the rate of change of energy. Okay. So the rate of change of energy of a given fluid particle, or if I am considering a finite control volume, the energy of the finite control volume will be keep on changing as it interacts with the surroundings. Similarly, if I consider a infinitesimal fluid element or infinitely small fluid element, the energy of the element, the fluid element, it will change with time as it interacts with the surroundings. So that is this term, the time rate of change of energy. Okay. Now here the model that we are taking is the infinitely small fluid element or infinitesimal fluid element, which is moving with the flow from one point to another point. So here the model we are taking is infinitesimal fluid element moving with the fluid. That is the model we are taking. Now that fluid element which we are considering, it will experience some rate of change of energy. It will experience some change of energy with respect to time. That is called the rate of change, time rate of change of energy. Now why this happens is given on the other side. This happens because of the net heat added or heat flux into the element. Okay, there is a heat transfer into the element and heat transfer out of the element. From one side heat will be added, the other side heat will be removed. So what is the net heat flux that is remained inside the fluid element? So that is the one part. The other part is the net rate of work done. So there are a number of forces acting on the fluid element, as we have discussed in the last discussion on momentum equation. Now these forces, they will do some work on this fluid element. Okay, so these forces, the surface forces or the normal forces, they will do some work on the element, because of which the energy inside the element will also change. So that we'll see. Now this will come again at the end of this slide. What is the time rate of change of moving element? Okay, this is the again I am saying the element which is moving with the fluid. That is the model we are taking. Now the time rate of change of element is given by the substantial derivative dE by dt. If E is energy per unit mass, then we have to multiply that with the mass, that is rho into delta x into delta y into delta z. Now we'll see the energy. This energy will have some parts, that also we'll see. Now we'll discuss again about the each term in that equation. The EQ, sigma q, represents the net heat added or removed from the fluid element. Okay. Now what is sigma w? It is the net rate of work done by the surface flow forces or the normal forces on the fluid element. Now the rate of work done on the control volume or fluid element in x direction is equivalent to the product of the surface forces with the velocity component. So we are considering the x direction. Okay, if I consider the x direction, the component of velocity in the x direction is u. Now if fx is the force in x direction and u is the velocity, then the product will give the work done. So that is the meaning of this statement. Now we will see this energy equation derivation step by step. Now what we are doing, we are considering fx. What is this fx? Fx is a part of f. Now what is this f? F is the body force per unit mass. F is body force per unit mass. Now Fx is, F can be written as Fx in I plus Fyj plus Fzk. Like that you can write. Now if Fx, if we consider Fx, we have to multiply that Fx with u. Now if I consider Fy, then I have to multiply with v, small v. Okay. If I consider Fz, I have to multiply with w. Now the total is Fx into u plus Fy into v plus Fz into w. Now how we'll get this? What is v? V, we know it is a vector quantity and it is ui bar ui plus vj plus wk. These ijk are unit vectors. You can write a bar here indicating it is a vector quantity. Now if I put f dot v bar, what I will get? I will get fx into u plus fy into v plus fz into w. So this is the total work done by the body force in three directions, and this can be written in a vector form like this. So that is what we are writing. The volume of the element is delta x, delta y, delta z. Delta x is the dimension of the element in x direction. Delta y is the dimension of the element in y direction. Delta z is the dimension of the element in z direction. So the three dimensions, if I multiply, I will get the volume of the element. Now the mass of the element will be obtained by multiplying the density with the volume, and that is this is the density. Okay, this is the density into volume. If I put, I will get the mass. The mass per unit volume is F. So the total body force is rho into F into delta x into delta y into delta z. Now what is the work done here? Work done already we have seen, it is a force into velocity, the dot product of force and velocity. Now here rho is a scalar quantity, the delta x delta y z is a scalar quantity, only f is a vector, v is a vector, so we are taking a dot product between these two elements. Now this will give the total work done by the body forces in x, y, z direction. Okay, this is not only in one direction, it is the vectorial sum of the anyhow it is becoming a scalar product because we are taking a dot product here, so it is a scalar component. So the net work done by the body forces in three directions is given by this equation. So the work done by the body forces we obtained. Now what we have to do, we have to see what is the net work done by the surface forces and the normal forces. Now we will see what this surface forces and body forces doing to the element. This we have already seen in the last class. Now here we have shear and normal stresses acting on the fluid element. Okay. What these stresses are doing, they are inducing a time rate of change of deformation. Okay. In the last class, the momentum equation also we have seen The normal forces, they will try to give a linear deformation. The shear forces, what they will do, they will try to give a angular deformation. Now, because of these forces, what happens to the element actually? Now, we will see the shear stress. Then shear stress is tau xy or tau yz or tau xz or tau like that. It is a combination of two directions, x and y or x and z like that. Now the shear stress, what it will do, it will give a shearing deformation. Okay, the shear stress will give a shearing deformation, and the normal stress sigma xx. So normal stress means you will write x both, it is acting in one direction and varying also in the same direction. But the shear stress, if you see, it acts in one direction but it varies in the other direction. Now this normal stress, what it is doing, it is changing the volume of the element. Okay, the normal stresses are causing the change in volume of the element, and the shear stresses are giving some shear deformation as shown in this diagram. So this is because of the normal stress, there is change in the volume, and because of the shear stress, what is happening, there is a change in it is causing a shearing deformation. Okay, now here you can see, here this is a velocity u, and after a distance delta y, what is the velocity u, and here this is velocity v acting in this direction, and at a distance of delta x, what is the velocity value of the velocity. Now because of this, what is happening, this additional velocity, what is this additional velocity, what is the velocity, it is the relative velocity between this point and this point. What this relative velocity is doing, it is giving some angular deformation. Similarly, this is the relative velocity between this is the relative velocity between this point and this point. Now this relative velocity is giving some angular deformation. So the velocity into this this is the relative velocity, the relative velocity into time, if I put, I will get to the angular deformation, and that is given by this beta here, and here it is given by alpha. Now here what it is doing, if the velocity is changing in the linear direction, what it is doing, it is causing some increasement in the volume. Okay, so that is the effect of this normal stress and shear stress. Now as a result of both shear stress and normal stress depends on velocity gradients in the flow. So both the shear stress and normal stresses, they are dependent on the velocity gradient. Here you can see, this is the velocity gradient, this is the velocity gradient, here this is the velocity gradient, and this is the velocity gradient. The normal stresses are dependent on velocity gradients, and the shear stresses are also dependent on the velocity gradient. Now in general, the normal stresses, okay, the normal stresses will cause very small deformation. Okay, the volumetric deformation caused by the normal stresses in normal conditions is very small, and so it can be neglected. But in case of the shock wave, okay, when you are considering the shock wave, the velocity gradients are very much high, that we cannot neglect these velocity gradients. Because of this, the normal stresses are also taken into consideration for our derivation, for our solving the problems when you are considering the shock waves. Okay, so this is about the normal stresses and the shear stresses, what are their effects and what they are dependent on, uh, for the deformation in a fluid element that we have discussed. Now we'll see, this is the fluid element. I have taken three same elements, but I have given the representation of the pressure force in this diagram. I have given the representation of the heat in this diagram, and here I have given the representation of the normal stresses and the shear stresses, what they are doing to this element here. Okay, now here if I consider this, first we will consider the shear stresses and normal stresses, what they are doing to this element. Now the shear force, the stress into area will give shear force, and into velocity will give the work done. So this work done, now sigma xx is the shear stress on this left side element. So the left side element, the normal stress is sigma xx. So the right side element, the normal stress is sigma xx plus dou by dou x of u into sigma xx. Okay. Now here both u and sigma xx are changing in x direction. That is why we have taken the partial differentiation of u and sigma xx. Okay, now the u into sigma xx into area, if I put, I will get the work done in on the left face. Okay, the work done on the left face I will get. Now this is the uh, what you say is the stress and velocity product. Because this product is changing in x direction, I have taken here dou by dou x of u into sigma xx, and this is the change per unit length. The change per unit length, change per unit length is given by dou by dou x of u sigma xx. Okay, this is the change per unit length. Now what is the net change? Net change is equal to change per unit length into the length in that particular direction. So what is the length in that particular direction? Here it is delta x. So this is the net change. So the net value in the on the right face is given by this, the net shear stress and velocity product into the area normal to that face. What is the area of this? This is this delta y, and this is delta z. So what is this? This is z direction. So this is delta z, this is delta y, and this is delta x. These are the three values. So I will write in a simple one. So this diagram is a little complex. I am writing here. This is delta x, this is delta y, and this is delta z. So these are the three magnitudes of this element in different directions. Now what we are taking is this left face. The left face, the height is delta y, width is delta z. So the area is delta y into delta z. Now this is the work done on the right face. This is the work done on the left face. This is work done on the right face. This is the positive direction. So this is a positive value. This is a negative direction. So this is a negative value. Okay. Now we will see about the shear stresses. The bottom face, if I consider the bottom face, I have the tau yx. Now what is this tau yx? Tau yx is the shear stress which is acting in x direction. In which direction it is acting? It is acting in x direction, either positive or negative. Negative direction of x direction. But it is varying in which direction? It is varying in y direction. So it is a acting in x direction and varying in y direction. So since it is varying in y direction, what I will write here, what is the change per unit length? It is tau yx. It is changing in y direction, so I have to put here y. So it is a dou by dou y of tau yx. Now what is the net change? So the net change, if I have to write, what I will get? I will get, this is the change per unit length into what is the distance in this direction, y direction. It is a delta y. So this is the net change in the product of u1 tau xy in y direction. So the shear force acting on the bottom face is u into tau yx into the, what is the area of this face? The area of this face is length is delta x and the width is delta z. So the area is delta x into delta z. So I can write this as u into tau yx into delta x into delta z. Now the same thing is acting here, and what it is here? Now here the tau u into tau yx plus dou by dou y of u into tau yx into delta y. So this is the net product of shear stress and velocity in top face, and the area is same, it is delta x into delta z. Now this is the shear force on the top, the work done by the shear force on the top surface. Now what is the sign, whether it is positive or negative? Now this is acting in negative x direction, so it is a negative value. This is acting in the positive direction, so it is a positive value. Now if I consider the front face and back face, so the back face, the velocity is u and the shear stress acting in x direction is tau zx. What is this tau zx? It is the shear stress acting in x direction and varying in z direction. The u into tau zx into delta x delta y. So this is the work done by the shear stress in on the back face. So since here it is starting and it is increasing in this direction, the back face will have a less quantity and the front face will have a greater quantity. Now this is varying in this direction, in the z direction. So if this is varying in the z direction, what I have to write here? The change per unit length is given by tau zx by delta z. Tau zx by delta z. Now what is the net change? Net change is equal to change per unit length into total length. So the change per unit length is tau by dou z of tau zx. Now what is the length in z direction? The length in z direction is delta z. So the net change is dou by dou z into tau zx into delta z. Now what is the area normal to this? Area normal, area of the front face, because it is acting on the front face and back face. So the front face area is delta y into delta z. So it is, sorry, delta y into delta x. So it is a delta x delta y product. Now what is the sign of this? On the back face, it is acting in the negative direction, so it is a negative value. On the front face, it is acting on the positive direction, so it is a positive value. So these are the different different works that are done by the shear stress and normal stress on the fluid element. Okay, now we will see. I'll recap this again. Pictorially I have explained. I am writing here in statements. In x direction, okay, we are considering in the x direction. So the tau xy denotes the stress in y direction and plane perpendicular to the x direction. So that is what is given. On the bottom face, the u xz into delta x into delta z. So on the top face it will be u into tau. It is x actually. Okay, it is x. It is not z. It is x. Now u into tau yx on the top face, and bottom face it is u into tau yx. Now it is dou by dou y of u into tau yx into delta y into delta xz. So this is what we have discussed previously. Now what we have seen is this one. So this is on the right face and this is on the left face. So the right face is positive, the magnitude of the left face is negative, and the top face is positive, the bottom face is negative, work done on the bottom face is negative, the work done on the front face is positive, the work done on the back face is negative. So if I add up all these things, what I will get is this one, this one, this one will be eliminated by these values. And now what I have to do, I have to consider the pressure force. Okay, we will see the pressure. Now the pressure force U into pressure into delta y delta z. And similarly here it is a U into pressure into dou by dou x of pressure into U into delta x. So we will see here, I will write here. I am considering only one phase. So this is the pressure force. What is this pressure force is doing? It is trying to compress the element. So the pressure force is trying to compress the element in both the directions. Here the velocity in x direction is u, the pressure is the P is the pressure. Pressure into what is this area normal to this x direction? It is delta y delta z. Now what is the pressure in this direction? It is u into p plus, it is changing in x direction, it is dou by dou x of u into p, so into delta x. So this is the net pressure on the right side. So the pressure on the left side is u into p into u into p. Now the on the right side the product of u and p plus dou by dou x of up into delta x. Now what is the area here? It is again delta y delta z. Now this is the positive x direction. So this is a positive value and this is a negative value. That is what is written here. So if here this is value and this value will get cancelled. So I will be remaining with minus dou by dou x of up. Now the this is the work done by the normal stress, the net work done by the normal stress. This is the net work done by the shear stress, and this is net work done by the pressure force. We have seen the net work done by the body force. We have seen the net work done by the pressure force. We have seen the net work done by the shear force. And the delta x, delta y, z is common, so I have taken it common. Now, what we have done till now is, it is in x direction, sigma xx, sigma yx, sigma zx, that is in x direction. Now the pressure force in, the work done by the pressure force in x direction. Now if I want to similarly find out for the other directions, what I have to do? Here sigma, in place of sigma I have to put xx plus I have to put yy, and here in z direction I have to put zz. Okay. Now here what happens to the shear stress? Shear stress, we are talking about the y direction and varying in x direction. Shear stress acting in y direction and varying in z direction. Now here shear stress acting in z direction and varying in y direction. Shear stress acting in z direction and varying in x direction. So if it is varying in x direction, I have to take partial differentiation with respect to x. If it is varying in z direction, I have to differentiate with respect to z. Okay. Now this pressure is varying in y direction, so I have put dou y here. This pressure is varying in z direction, so I put z here. So here sigma zz is varying in z direction, so it is a why it is varying in z direction, because it is acting normal to the z direction. So it is acting in z direction and varying in z direction. The normal stresses and the pressure forces, they are acting in z direction or acting in x direction and varying in x direction. Acting in y direction and varying in y direction. Acting in z direction and varying in z direction. But the shear stresses, they will act in one direction and vary in other direction. So the y direction forces and y direction work done, z direction work done. And this also we have seen this net work done by the body force. Now we will see the other term, the heat transfer term. The net flux of heat into the element. Okay. So the how this heating happens, that we have to see. So there are two things. One is volumetric heating. Okay. Volumetric heating is done by the radiation component of heat transfer. Either the radiation it is absorbing or radiation it is emitting. The fluid element, it is having a potential to absorb heat radiation or emit heat radiation. So this is resulting in volumetric heating of the element. Okay. Now the other component is the heat transfer across the surface. Okay. The heat transfer across the surface is because of the temperature gradient. Previously we have seen the work done by the normal stresses and shear stresses, they are because of the velocity gradients. Similarly here the heat transfer across the surface is because of the temperature gradients. Now this is defined as thermal conduction. The heat transfer across the surface due to the temperature gradients is defined as the thermal conduction. Now if Q dot is the volumetric heat transfer or heat added or heat rejected per unit mass. Volumetric heat added or rejected or the heat transfer per unit mass is Q dot. Now, what is the total mass of the fluid element? Mass of the fluid element is equal to volume into the density. So, the volume into density will give the mass of the fluid element, and this is the heat transfer, volumetric heat transfer per unit mass. So, the product will give the net heat added because of radiation. So, this is the volumetric heating is because of the radiation component, and that is given by Q dot into mass of the element. Now we will see the heat added in z direction, in x direction, y direction, z direction. We will see again the diagram. So this is the diagram. So this is heat is adding here, heat is getting into the element, and heat is coming out of the element. Okay. So the same diagram I will draw here. You can see here. Now here what is happening here? The heat is added to the element and heat is rejected from the element. Now Q dot x if I take, that is heat added in x direction, and which direction it is changing? It is changing in only x direction. So it is written here as dou by dou x qx plus what is this, dou by dou x of qx dot. So this is a heat transfer, change in heat transfer per unit length. So the total change is into delta x. So this is the total heat transfer rate on the right phase, and this is the total heat transfer rate on the left phase. So the left face one is acting in a positive x direction, so it is positive. The right face one is the right face one is leaving the element. So this is the work, the heat is added to the element, and the heat is heat rejected by the element. So what is the amount of heat remaining in the element is given by the amount of heat added minus amount of heat rejected. So what is given? This is the amount of heat added and this is the amount of heat rejected. So it is given by minus dou by dou x of q dot into delta x into delta y into delta z. Similarly, if I do analysis in y direction and z direction, I will get dou by dou y of q dot y and dou by dou z of q dot z. So this is the net heat added or net heat conducted in the three directions into the element. So if the heat is more is rejected, I will get a negative sign. If it is the heat transfer added is more, then I will get a positive sign. So here what we are taking, the heat, more heat is rejected, so I am getting a negative sign. Now we will see one law called Fourier's law of conduction. The Fourier's law of conduction, what it states is the net heat transfer rate is in x direction is proportional to the temperature gradient in x direction. So heat Qx is proportional to temperature gradient in x direction. Now, what is this constant of proportionality? The constant of proportionality is nothing but the thermal conductivity. Okay. Now, the generally heat transfer happens in the from higher temperature to lower temperature. Heat transfer happens from higher temperature to lower temperature. So the temperature is decreasing in this direction and heat is transferring in this direction. That is why we will put a negative sign here. So the heat transfer due to conduction in x direction is equal to minus K. If it is a isotropic element, that means the conductivity is constant in all directions. I will write K. Otherwise, I will write Kx, Ky, Kz. So, we are simplicity, we are taking the conductivity of the element is same in all directions. So, it is minus K into dou by dou T by dou X. If I substitute this minus K into dou T by dou X here, I will get dou by dou X of K into dou T by dou X. Similarly, if it is Y, I will get here Y. If I substitute that here, I will get K into dou T by dou Y. If I substitute for Q dot Z, I will get K, dou by dou Z into K into dou T by dou Z. So, this is the net heat added into the element or net heat flux into the element. Okay. So, this is the net heat added and previously we have seen net work done. If what is the total change in energy of the element. So the energy of the fluid element is having two parts. One is the internal energy. Okay, the internal energy of the element and the kinetic energy of the element. So two things are there: internal energy plus kinetic energy. So if E is the internal energy of the element per unit mass, then E into total energy is E into delta X, delta Y, delta Z. Now, if kinetic energy per unit mass is V square by 2, what is the total? And sorry, here it is unit mass, so I have to multiply with rho here. Now, if this V square by 2 is the kinetic energy per unit mass, what I will get here, rho into delta X, delta Y, delta Z. Now, this is a constant, it is not changing with time, density is not changing with time. So, what is changing? E and V square by 2 are changing with time. So, rho and delta X, delta Y, delta Z were taken outside. The time rate of change of any quantity is given by the substantial derivative. That is why it is given as d by dt of the sum of internal energy and the kinetic energy. So this is the time rate of change of energy of the element. So the time rate of change of energy of the element. So we'll see the change in internal energy. Okay, the change in internal energy of the element plus changing kinetic energy of the element will give the time rate of change of total energy of the element. So what we have seen till now, we have seen the time rate of change of element energy of the element is equal to the net heat transferred into the element plus the net work done on the element. So if I add up all these three things, I will get this equation. So this is the time rate of change of energy of the element, and this is the net heat transferred due to conduction. This is the net heat transferred due to the radiation, and this is the net work done by the shear stresses. This is the net work done by the pressure force. This is the net work done by the shear stresses and normal stresses, and this is the net work done by the body forces. So if I add up all these things, I will get the energy equation, which is a non-conservative form. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.